Imagine for a second that you are holding, say, $50 million in your hand, not in a bank vault, not in a secure government bond, but in a digital wallet that only you control. You need to send that money to a safe location. Say, you copy the address, you paste it, you check the first few numbers, you check the last few numbers. It looks perfect. You hit send, and in a single second, $50 million vanishes into thin air. It's gone forever. This isn't a hypothetical nightmare. This is actually happening, and it happened recently to a sophisticated investor. But here is the part that keeps me up at night. It wasn't a hack. The code didn't break. The password, it wasn't stolen. No. The system worked exactly as it was designed to work. And that is the terrifying reality of the current crypto infrastructure. But what if I told you that this specific catastrophe is structurally impossible on a different network? Because today we're going to look at how the internet computer, or ICP, the world computer, completely eliminates this $50 million mistake. We aren't looking at a patch. We are looking at a completely different way to build the internet. So we spend so much time looking at charts and arguing about market caps that we often miss the most boring but yet dangerous part of this industry as a whole, the plumbing, underlying infrastructure. Because so when you look at the recent $50 million loss caused by address poisoning, it is easy, and I'm saying very easy, to blame the user. It is easy to say they should have been more careful, but that is a lazy way to think. Is that just say if a system requires you to be lucky every single time you use it, it is a bad system. And today we're going to take a walk through the architecture of money. We are going to look at why Ethereum and similar L1 chains rely on a design from the 1970s that leaves the door open for these attacks. And we are going to contrast that with how Definity and ICP, the world computer, rebuilt the entire stack to close that door shut. We aren't just talking about a software update here. We're talking about a fundamental difference in how we define ownership on the internet. And by the end of this video, you will understand why the next wave of global adoption cannot happen on systems that rely on copy, pasting random strings of text. We are going to explore the difference between digital cash and a true digital platform. And we're going to do it by looking at the nuts and bolts that keep the building standing. The $50 million loss I mentioned at the start is known as an address poisoning attack. And to understand why the internet computer is different, we first have to understand the trap that exists right now. And here's how the trap works. Just say, on networks like Ethereum, your identity is a long, ugly string of just random numbers and letters called a hexadecimal string. It looks like, say, gibberish, pretty much, to sum it up, because it's so long and impossible to memorize. Nobody types it out. Everyone just copies and pastes it. Hackers know this, obviously. They know you are lazy. They know I am lazy. So they create vanity addresses that look almost exactly like yours. So if your address starts with, say, 0x45 and ends with 99B, they use a computer to generate an address that also starts with x45 and ends with 99B. But the middle, the part you don't read, is totally different. Then they send you a tiny transaction, maybe $0, a few cents. This puts their fake address into your transaction history. So the next time you want to send money to yourself, you go to your history. What do? You see that address looks familiar, you copy it, and you send your life savings to a thief. It's simple as that, because this relies on human error. And human error is a one thing you can never patch on a legacy chain. there is no solution to that. From my time observing in traditional finance, working in the industry, from the markets, I learned something very important about high value transfers. I could tell you in the old world of wire transfers, if you get a single digit wrong, say on an account number, the money doesn't usually incinerate. It gets stuck. It gets flagged. But why? Because the name on the account has to match the number. So there is a semantic check. So the system asks, does this number belong to, say, John Doe? If the answer is no, the transfer fails. In the early days of working, say, with institutional systems, I remembered watching a veteran trader, old timer, almost make massive error. He had the wrong code for a counterparty, but the system stopped him. And I'll tell you why they stopped him, because the settlement instructions didn't match the destination identity. It wasn't about him being, say, smart. It's got nothing to do with that. It was about the system being safe. Traditional finance is slow and it's expensive, yes, but it has safety nets. Crypto removed the safety nets to get speed, but it kept the risk, which is underlying. And this is where the architecture of the internet computer changes the game completely, because it just doesn't ask you to be more careful. It removes the need for the copy-paste ritual entirely. So let's look at the first major difference. Obviously, no copy-paste addresses. On ICP, the model for identity is completely different. It uses something called internet identity. And say instead of a long string of text that you have to, say, safeguard, you authenticate using the hardware you already own. The fingerprint scanner on your laptop, the Face ID on your phone, or a YubiKey. Think of it like this, okay? When you want to call your mother, do you type in her 10-digit phone number every single time? I doubt it. I'd say no. You click mum, say in your contacts. Your phone handles the rest. It just routes it and then makes a call. You trust the connection because the identity is bound to the contact, not to the raw numbers. And in the Ethereum world, we are still typing in the 10-digit number every time, or rather copying it from a piece of paper we found, say, on the sidewalk or in the cupboard. ICP moves us to the contacts list era of blockchain. So when you transact, you're interacting with a cryptographic identity, a principle that is authenticated by a device. There is nothing visual for a hacker to spoof because you aren't looking at a string of text. You are looking at a verified session. The attack surface for poisoning, say, a text string, disappears completely because the text string isn't the primary interface anymore. So this brings us to the second pillar of this architecture, which is key here. It's a canister-based ownership versus externally owned accounts. Okay, because in most blockchains, layer ones we're talking about, everyone is an externally owned account, or EOA. So this is just a fancy way of saying anonymous person with a private key. So every account looks like the same. A hacker's account looks exactly like a legitimate exchange account. On ICP, assets and applications, they live in canisters. A canister is like a smart contract, but here on steroids. It has memory, it has state, it has, and most importantly, it has explicit interfaces in all this. And let me give you a real world analogy to make this stick. So imagine you are delivering, say, a package. In the Ethereum model, you are dropping, say, a box of cash on a specific GPS coordinate, say in the middle of a field somewhere randomly. If you're 1 inch off, or if someone, say, changed the coordinate, say on your map, you drop the cash in the wrong spot and it's gone. You've lost it. You don't know who picked it up. In the ICP model, you aren't dropping cash, say, at a coordinate. You are walking into a building, a specific building, with a sign on the door. You are handing the package to a receptionist. The building is the canister. It has code embedded. It has rules embedded. You know exactly which application you are interacting with at all times. Attackers cannot inject a lookalike canister into your workflow easily because interacting, say, With a canister, it requires calling a specific method or function. You aren't just sending tokens, say, to an address, because you are engaging a function. And this leads directly to the third point in all this, the signed method calls. Because instead of blind transfers, so when you send, say, money on a standard blockchain, okay, the network only checks one thing. It checks, is this address format valid? It doesn't care if the address is a black hole. It doesn't care if it's a thief. It just checks the math of the address format. On ICP, every transaction is a signed call to a method on a target canister. And this, I know it's a bit technical, so let me break it down simply. Imagine you are signing a check, okay? In the old crypto world, you are signing a blank check and hoping the person holding it is honest. In the ICP world, the transaction itself includes instructions. I am authorizing, say, this specific canister to take these specific tokens and move them to this specific balance. So if you try to send funds, say, to a destination that doesn't have the right method to receive them, the transaction doesn't just burn your money, it fails at a semantic level. The system says you're trying to call a deposit function on a calculator app. That doesn't make sense here, and it just stops. I can tell you, I remember a situation, it was a while ago, when I was working in traditional banking operations. We had to manually approve large wire batches. There was always a purpose of payment code. So just say if the code was purchase, say, real estate, but the destination account was, say, a known gambling entity, so the compliance software flagged it. It triggered it immediately. It wasn't about, say, the money itself. It was about the logic not adding up. And ICP brings that logical check into the blockchain layer itself. Now let's talk about this specific trick that hackers used in the $50 million theft here. Pausing their history, the victim in that story copied the address from their transaction history, went into there, copy and paste, and the hacker had spammed that history with fake transactions to plant a trap within the history. On ICP, the wallet history works differently, completely differently. It isn't just a raw feed of everything that happened on, say, a particular day on a particular chain, because the wallet is often a canister itself or interacts with specific indexes. It can filter out noise. Think of, say, your email, okay? Inbox. You have a primary tab and a spam tab. Google knows that just because someone, say, sent you an email, okay, offering, say, cheap pharmaceuticals, for example, it doesn't mean you want to see it next to an email from, say, your boss. Most blockchains, okay, today are like an email inbox. No spam filter. Everything shows up in the main feed. Just say if a hacker sends you dust, it sits right next to your $1 million transfer, for example. And ICP's architecture allows wallets to treat history as application managed state. This means the wallet can say, okay, I didn't ask for this, okay? Inbound transfer. I don't know who this sender is. I am going to hide this information from the user's view. By quarantining unsolicited transactions, the user never sees the fake address. And if they don't see it, they can't copy it. If they can't copy it, they can't lose the money. So it is a subtle change, but I can tell you from a structural perspective, it is massive. It completely changes the user experience from, say, user beware to system protected. We have talked about the user experience, okay? The front end door of the house. But to truly understand why this holistic architecture changes the risk profile for institutions and individuals, say, we have to go down into the basement itself. We have to look at the actual structural foundation. This brings us to a concept that is often thrown around, yes, but rarely, and I mean rarely understood, chain key cryptography. Say, in traditional blockchains, if you say lose your private key, you lose your assets. They're gone. It is a binary outcome. The network doesn't know you. No, not at all. It only knows the key. Just say if a bad actor gets the key, the network assumes they are you. And this is the single point of failure that keeps chief risk officers at, say, major banks awake at night. And I'll tell you why. Because I do recall a specific instance during my time working with an institutional custody solutions. We spent months designing a key ceremony. It involved Faraday cages, gap laptops, and 3 different executives flying to 3 different continents just to generate a master key for a settlement layer. And the operational overhead was massive. But why was it massive? Because the institution was terrified of that single point of failure in all this. The internet computer solves that issue. This is with something called threshold relay. It's very underestimated, and here's how it works. Without the math jargon, instead of, say, one key held by, say, one computer or one person, the key to the network is mathematically split into pieces. These pieces, okay, they are distributed across independent node machines running in data centers all over the world, random destinations, random locations. To sign a transaction or approve a state change, a threshold of these nodes must, and I mean must agree, they must collaborate to assemble the signature. But here, and this is the magic part, the full key is never, and I mean never assembled in one place. It exists only as a mathematical concept, never as a physical file that can be stolen. And you know what this means? An attacker cannot just hack a server and steal, say, the root key from that of the subnet. They would have to, say, think of it like this: hack multiple data centers in different jurisdictions around the world in different locations, all simultaneously within milliseconds. And from a security engineering perspective and even logical sense, this raises the cost of an attack from difficult to economically impossible, like statistically speaking. And now let's widen the scope to the industry, say at large here. When we look at the data, say, regarding crypto hacks, a massive, and I mean a massive percentage of losses, I'm talking billions of dollars annually, comes from one specific vector: bridges, dependencies. A bridge is what connects, say, 2 blockchains. And say if you want to move Bitcoin, say, to Ethereum, you typically wrap it. You lock your Bitcoin, say, in a vault, and a bridge issues you a fake Bitcoin on Ethereum. And the problem in all this, that bridge is a honeypot. Just say, if the bridge is hacked in between, the backing asset is gone, and your wrap token becomes worthless. Historically, I can tell you, data suggests that, say, cross-chain bridges are the weakest link in the entire crypto ecosystem. In 22 alone, so we're talking 3 years ago, Chain Analysis report indicated that over $2 billion were stolen, specifically from bridge hacks alone. ICP introduces a different paradigm, I'm telling you, with native integration. Because of the cryptography I just mentioned, the Internet Computer Protocol can actually sign transactions on other chains. It can create a Bitcoin transaction natively. It can sign an Ethereum transaction natively. It doesn't need a bridge. It doesn't need dependencies. It doesn't need a third party. The ICP network itself, it acts as the wallet. But why does this matter to you and me? Because if you are holding, say, Chainkey Bitcoin and ICP, you aren't holding an IOU from, say, a startup that might get tomorrow, or you're holding an asset that is mathematically secured by the consensus of the entire network. And this eliminates counterparty risk. And in traditional finance, I can tell you this, counterparty risk is the danger that the person on the other side of the trade goes broke before they pay you. And I've seen it many times before, because in crypto, the bridge is the counterparty in all this. So by removing the bridge and the dependencies, ICP removes the risk. We cannot talk about, say, mass adoption or safety without talking about the economic model. So on Ethereum and most other chains, layer ones we talk about, every time, say, you want to move a muscle, you have to pay gas, okay? You need to hold Ethereum to move USDT. You need to hold, say, Solana to move USDC. And this creates a massive friction point. It forces users to go to exchanges directly, buy a volatile asset and keep it in their wallet just to pay for postage. Think of it like this. It's like needing to, say, own shares in the electricity company or the electric company just to turn on your lights. Makes me laugh. And from an institutional perspective, this is an absolute nightmare. A corporate treasury, say, does not want to hold, say, volatile cryptocurrency, say, on its balance sheet just to pay, say, transaction fees for a stablecoin payment. No. It creates tax events. It creates accounting headaches. I see it flips this model on its head with reverse gas. On the internet computer, the developer pays for the computation, not the user. The canister, the smart contract, is loaded with cycles, which are stable in cost. Just say when you interact with an app, okay, you interact with the app on ICP, you often don't even know you're using a blockchain. No, they don't pay a fee. You don't sign, say, a pop-up. No, you just use the app and you're good to go. And this mirrors a Web 2 model. So let's say when you watch a video on YouTube, you don't pay Google to fraction of a cent for the server bandwidth. Not at all. Google pays for the servers and they monetize you in other ways. And that's how it works. And by aligning the economic incentives with how the real world actually works and how it does business, ICP removes the dust problem. You don't need to keep, say, $5 worth of tokens in a wallet just in case, you know. This reduces the number of assets a user has to manage, which in turn reduces the surface area for mistakes. Because there's one final layer of the defense that is often controversial, but critical for stability and very critical. The network nervous system, or the NNS. Okay, because in most blockchains, okay, all those layer ones out there, if there is a catastrophic bug or a hack, the community has to argue on Twitter for weeks on ends about what to do. Say, should we fork? Should we roll back? It's a messy situation. It's slow. And during that time, uncertainty kills underlying value. The NNS is an algorithmic governance system that manages the internet computer. It acts like, say, the brain of the network. It can upgrade the protocol without a hard fork. Think of it like this, okay? An automated, say, IT department, okay? In traditional banking software, we had to, I remember, patch. Say, we had our patches on Tuesdays, okay? We would take the system down, install security updates, and bring it back up to life. The internet computer upgrades itself while running the whole time. It identifies efficient routing. It manages nodes, machines, and yes, in extreme theoretical cases, it provides a venue for the community to vote on how to handle malicious canister behavior without no downtime at all. Some purists argue this is decentralized, but from an enterprise perspective, this is recoverability. Institutions cannot put, say, billions, trillions of dollars on a rail that cannot be fixed. If it breaks, they need a process, and the NNS provides that process fully on-chain, 100%, transparently and algorithmically. Let's contextualize, okay? This, say, with a story about settlement finality. So in the early 2000s, I watched the transition from paper stock certificates to digital entries. People were terrified, okay? They said, if I don't have the paper, I don't own the stock. What calmed them down was the concept of central securities depository, the DTCC, a massive central ledger that everyone agreed was the truth. Blockchains, okay, are trying to be the DTCC for the entire world. But the problem here is that most of them operate on probabilistic finality. This means, say, simply said, if you send a transaction on Bitcoin, you are pretty sure it's done, okay, after 10 minutes. You're very sure after 60 minutes, but it's never 100% instantly. That's the issue here. ICP operates with something closer to deterministic finality because of the consensus mechanism that's underlying. Finality happens in 1 second or under, but why does this matter for security? Because the gap between, say, the transaction sent and transaction finalized is the zone of uncertainty. This is fundamentally overlooked. That is where front running happens. That is where price slippage happens. This is where anxiety leads to errors. By closing that gap to 1 second, 2 seconds, ICP mimics the speed of a Visa swipe, but with the settlement assurances of a wire transfer. And we are moving toward a point where the word crypto might disappear from the user's vocabulary once and for all. When you use the internet today, you don't say, okay, I'm about to use TCP IP to send an email. No one says that. You just send an email. That's it. You do it without thinking. The protocol faded into the background completely because it worked. It's simple. But the $50 million address poisoning attack happened because the protocol was in the foreground and the user was fighting the protocol here. The user was wrestling with hex strings, limits, blind signing. The architectural shifts we have explored today with internet identity, canister logic, chain key cryptography are all designed to push the protocol back into the background. When a system is designed correctly, safety is the default state, not the reward for being an expert. I've seen this evolution before in my industry, going back in my early trading career, I remember too, people were trading, even heard the stories from my old friends. They were trading in the pits, all the papers waving, errors were rampant. They were telling me people lost millions because they misheard a number in the trading pits. You know what I mean? Then we moved on to electronic trading that took over. The noise stopped. The errors dropped down dramatically by 99%. I had friends that worked in trading pits in the US and the volumes exploded that way. And crypto is currently in its screaming in the pit phase. We are waving paper tickets, hex addresses, and making manual errors. And those manual errors were crazy back in those trading days when they were trading physically in the pits. The internet computer is the move to electronic trading. It is a sterile, silent, efficient server room where the rules are enforced by code, not by hoping everyone hears you correctly. So ultimately, understanding here the mechanics of the internet computer can completely, and I mean completely, change how you approach the concept of security in crypto, okay? Because we often think security as means of having, say, a longer password or, say, a better hardware wallet. But true security is architectural. It is about removing the option to make a mistake. The key lesson here is simple, but I can tell you powerful. Structure matters more than behavior. You cannot, say, train millions of people to never make a mistake. Humans, okay, get tired. We humans, okay, get sick. We get distracted. I've been sick the last week. But you can build a system that refuses to accept a mistake. That's for sure. Because this perspective might just shift the way you see the entire blockchain space as a whole. Because it isn't just about, say, which coin goes up or the price. No. It is about which network can actually carry the weight of the global economy without dropping it, without compromising it. Think about this the next time, say, you encounter a long, confusing hex address. It could be, and it could make all the difference between a secure future and a catastrophic loss. And that's the story behind the architecture of safety on the ICP world computer. It's not flashy. No, it doesn't make headlines until it saves you. But it is the foundation that allows, and I mean allows, everything else to be built on. With that, we wrap up today's journey into the underlying plumbing, because everything comes together when we see it from this angle. Not as a casino, no, but as a fortress. And stay curious and let your journey continue. Everything, and I mean everything we explore today, could change the way you see the digital ownership forever. It's easy, I can tell you, it's easy to get lost in the noise of the daily market moves. It's easy to chase the flashing lights, the bright lights, but remember, the choices you make today, say, about what you learn and what you understand, shape truly tomorrow's story. And if this video cut through the noise and actually gave you clarity and not hype, not herpium, then do 3 things right now. Hit like, so this reaches people who are tired of being misled. Subscribe, because this channel is, and I'm talking about, is about understanding underlying technology and where technology, money, and power are actually going before the headlines actually catch up, and comment with what clicked for you or what say you want broken down next. I read every single one, and if you want the signal instead of noise, perspective instead of panic, and clarity before consensus, subscribe now. And if this video inspired you, also give it a like and share it with others. Get it out there because many need to see the truth, and drop a comment below. I want to hear your thoughts and experiences also. And don't forget to subscribe and turn on notifications so you'll never miss the next adventure we go on. That is key here. And more importantly, stay decentralized, and I will see you on the internet. Computer, have a good Christmas. Enjoy the festive period. Have a good holiday. Keep well. Until next time.